So when we start to talk about the event streaming architecture, we haven't talked about, there's been no details so far. It's high level so far. So let's start to get into a little bit more detail now. One, we need to understand what a producer is and what is consumer from a very high level, right? So producers are essentially any application, when you write your apps, any apps that you write that is able to produce data to the Kafka cluster, that's what we call the producer. If your apps are coming to read and consume the data from Kafka, we call them consumers. So if you have consumers, even if you're a consumer by yourself, you still need to give yourself what's called a group name. Let's say my group name there is HC1, something like this. Even if I'm by myself and I'm coming to the Kafka cluster to consume the data, I need to have a group name. And we'll talk about why it's necessary a little bit later, because this is how we scale. If I have a group name, later on, I can add another consumer, start it on the different container or wherever, but as long as it has the same group name, which is just a string, then this Kafka puts them together like this. They consider to be in the same group. That means the rules will apply to how they process the data from Kafka cluster. So if the consumers have the same group, if they have the same name, they're part of the same group. This is what's called the group ID, right? Group ID. And if the consumers have the same ID, that means they work together. So for right now, what I want you to feel comfortable with is this concept that producers are applications that will produce data to the Kafka cluster. Consumers are applications that will come and consume the data from Kafka cluster. And if someone said, well, what is the Kafka cluster? Remember, the Kafka cluster is the cluster that is made up of what's called brokers. That means when you download the software bundle, you download the software bundle to each system, but you turn on only the one that says, I want to be a broker. You turn on only the broker software, because in a production environment, we want the services to run on separate machines. So this is the broker, and every broker will have a name. So let's say this is broker 1, and it listens to port number 9092. This one would be broker 2, listening to port number 9092. All of them listen to the same port, because remember, it's a software that uses, just like SSH uses the port number 22, right? So if you start SSH on your system, you're still going to use port number 22. I'm going to use port number 22 if I'm running SSH. So the broker software, regardless of where it runs, uses the port number 9092, unless you change it, but there's no reason to change it unless you have some. So this will be broker 4, 9092. So the broker will be separate from other services in your production environment. So now when you write messages, these brokers are here. They're a distributed collection of systems. When you connect to any one broker, like if I connect to broker 1, then I will be able to know exactly all the information about broker 2, broker 3, broker 4. In other words, it's like right now in this chat, let's just pretend that all of you guys are producers. If you're producers, when you write data, pretend that the chat itself is the Kafka broker software, right? So I'm going to ask you guys to pick any number between 1 and 20, and I just want you guys to just type it into chat just to be interactive. Any number between 1 and 20. So I see gang was the first one. So in this case, all of you guys are producers, and you will see that you're writing the data you're writing it to Kafka, right? And we'll look at this in detail, but the Kafka, there's a log that begins with offset 0, 1, 2. It's like an array. Always begins with 0, but we call these offsets. So the first number that came into chat, and Cedric has broken the application. He wrote a decimal number, but that's okay. Kafka doesn't care what it is, because Kafka would serialize it. So gang was the first one. This is the number 9 for gang. And then if you look at the numbers, there's 4 and there's 5, there's 11. So the next message that comes into the log would be the number 4, and then the next message would be the number 5. The next number would be 11, and you can see that the next one here would be 3. So if I ask you now, this message that is written to this log, what's the message, what at offset 1, what message is written to offset 1? Well, the log here, you see that is the number 4. What message is written to offset 3? You see here is the number 11. Hopefully this makes sense, right? If this little example makes sense to you, what you just did, know that this information will be stored here on these brokers, and we'll see more detail about it. And then now if I'm a consumer coming to read this information, if I'm just one consumer coming from by myself and I want to read this information, then I will be reading and consuming all this data. I will be reading, oh, here's a 9. Oh, here's a 4. Oh, here's a 5. Oh, here's a 11. Oh, here's a 3. And now at this point, I am at the end of log. Well, let's say if that was the end, right? According to this example up here, let's say the 3 here. So the consumer will be consuming the messages from the log. Okay, any questions? Again, we will get more specific, but to start off with, does this make sense? Please let me know if I need to clarify. A lot of details to come, but I just want you to understand. So we have this concept, we said log is like an array, you know, like the index of an array, but we don't say index, we say offsets. And every message that comes is appended. First come, first serve. First one goes to 0, okay? So this is the whole general picture. Consumers in consumer group, you can have one consumer by itself, or if you have multiple consumers running with the same group ID, then they're in a group, and then they will have to process the data according to certain rules, okay? Remember, there are people new to this topic for the first time, so I want to start it with general, but it's going to get more specific, promise. Okay. So far, they said, look, the atomic unit of Kafka, when we're dealing with data, in other words, when they're talking about the atomic unit, in other words, they at the bare minimum, when people say record, they're also referring to like a message, right? Or people event. But literally, event is what generates these messages that will be basically stored as records in the logs, but people use them interchangeably. What do I mean? So for example, if I clap my hands right now, look, that was an event. I just clapped my hands. That's an event. Here's another clap, right? That's an event. If you had a way to measure that, then that value that you write, you take that, you measure that value and you store that. So you can say, oh, here's the event, or you say, well, here's the record, or here's the message. But essentially, you are going to record something into the file. And that's where, so the record has headers, optional, key, value, and timestamp, right? Typically in distributed systems, remember, Google made MapReduce very popular, working with key value pairs to be able to do the map and reduce. And over time, we find that it's very useful to work with key value pairs when we're working with data. So what do I mean by key value pairs? So for example, when we want to send a message, let's say, for example, we have a customer. Customer have a IRAS account that looks like this. Let's say we have customer 1, some IRAS X953, something that makes sense to your company. But let's say each customer ID is combined with some special internal code, and this makes up like the unique customer ID. But then this customer has records associated with it, right? So you want, let's say if we look at a record for this customer, we can say, okay, that's the customer ID, and we just put this here like this and say, look, here's a record now, and the record is going to have this customer ID as a key. I'll just put CUST-ID. We'll use that as a key, and then all the other information about the customer, like the customer has a date of birth, customer has a salary, customer has a location in Singapore, customer is the customer, maybe credit score, such as CS, and then all kinds of other information you could think about the customer written in here. So when I produce a record, all of this here is a record. And this is my key I'm using, and this is the value. And I want to be able to produce this entire record to Kafka. This is one record. Every customer will have a customer record like this. And your customer record could be as much as a whole page of data. Then the customer ID is the key, and this entire thing is the value, right? Does that make sense? Please let me know if that makes sense, because you'll see that we are going to be working a lot with records in Kafka, right? And messages, it's in record, and we need to understand this. We will see how Kafka makes use of the key and value pairs coming up. But first things first, does this make sense when I say, hey, if I have a customer ID, here's a customer, a unique way that identifies this customer, like customer one, or it could be Joey-Iris, whatever, X988. But it's always a unique, you determine what your key is going to look like, right? And then the value. So this is information. And think about it. Maybe all you care about, this is the business relevant data. And then it has a timestamp, like when was this message produced? So timestamps are very important in Kafka. So this is just saying, like, look, this is an example of what a Kafka record looks like. It's very simple, right? The data element is called the record. And you could call it record, a message, or you could say event. Those headers you see right here, they are optional, right? And you could have those, in other words, if you're a developer and you're working with it, maybe you want to have some information to tag a data center or something like that. You can do that. And all of this is in the API. And then, but this key and value is very important. And then you look at the timestamp. Like if I clap my hands right now, this is when the message just created. This is called the event time. But you can also say that that is the create time, the time the message create. That's the creation time. Creation time is when the message is actually created, when the client created the message. But then you say, well, what is this ingestion time? Because remember, you're the producer, you're going to send this message to the broker, right? You send the message to the brokers in your Kafka cluster. Typically, you have a minimum of 3 brokers. But when you send a message, you send a producer request and say, hey, broker, I'm making a request. Can you please store my message, right? And this broker will have to go ahead and store it for you. And we'll look at the details of that, but then it will send you back an acknowledgement. Well, that's optional as well. But this message that you're producing at this time, it has a timestamp, right? And when they talk about timestamp, just know that the create time is when the client creates the message, or you can say event time. And then the append time is when it makes it to this broker and is written into the log file on the broker. This is the append time. Or you could say that this is the log append time or ingestion time. Ingestion. So when the message is ingested or appended. Does that make sense? Please let me know if you have any questions related to that.
Can you hear me?
Yes,
Hussein?
I can hear you.
Okay. So my question about this timestamp is, it's the timestamp that is contained within the record is the time, say we have a producer. So a producer triggered this event to Kafka. That is the timestamp, is it?
Mm-hmm. Yep.
Am I correct to say it is the timestamp that the producer created the event and sent it over to Kafka?
Yeah.
And the broker, yeah. And the append time, the one that you said, which is recorded in the broker, is the time that this broker received a message from the producer.
Correct. Because when a broker gets it, the broker has to append it to this log. And so that's what we call the ingestion time or the append time. And then there's one more time that I didn't put here, but the last one is when the message is actually processed, and that would be the processing time.
Processing time is the time that the consumer read it, is it?
Correct. Perfect. When you're consuming and the event and processing that data. Mm-hmm.
But it is still recorded within the broker.
Well, no, because you have the processing time is when this is happening, when you're consumers, but the message has this event time associated with it, or the broker. If you want the broker to override the time, you can use the broker log append time. But just know that when you're actually processing this, that's when the processing time. But there's,
Okay.
yeah. So it's
And
important to
then this,
understand.
yeah, so sorry, go ahead, please.
No, that's pretty much it.
And then all of this timestamp is in milliseconds, correct?
Yes, typically we have most all of these values stem from the birth date of Unix, January 1st, 1970. And it's the milliseconds time from that time.
Okay.
So it's like when you do a date command on the Linux system and you see all that long, the huge number, that gives you the milliseconds since January 1st, 1970.
Yes, correct. Okay, thank you.
And now whatever format you use, you can change, but I mean, it stems from that. Oh, question, sorry.
Yeah, I just want to know, like, so for that specific timestamp, right? How do we know if that's a creation time or a appended time?
So you can choose actually by default, right? The default has this property that is the create time by default. But if you change the property, you say, hey, I want the broker to override it, then the broker will override that with the, in other words, it becomes a log append time. But by default, it's the create time. Or event time.
Like, so when I change the configuration in Kafka, like all records at the same time can only have a creation time. It cannot like have a mixture of, creation time and ingestion time, right?
Well, well, you can do, the thing is, you can configure that timestamp. That's a property that you can configure and you can set that property. And we haven't talked about topics specifically yet. So I will talk about, if you don't mind, there's one thing I'll talk about and I'll show you a lot more. There's so much more detail about it, but just know that for now, if you think about this, just know that when you create in a producer, if you don't specify a different time, then it's the create time. But the broker can always override that and make it the log append time. And so this is what, then the time is associated with the time the message actually is written to the log. And then we will see, I will show you a little bit more detail a little bit later. But for now, does that make sense? Just for now, just know like, yes, my event, this is event time. And then if you don't override it, that is the default. But if you do, then you can say, well, when did I get it? When did the broker get it and append it? And that's the append time or log append time. Just terminology for now. There's so much more I want to take you through before. Yeah, question?
Yeah, sorry, I just want to clarify. I think the timestamp, once it's already in the record, it's immutable. That means if you change the broker property, that only affects new records. Whatever ingested in the past, the timestamp will be whatever it is in the system.
Right. So you are correct. In other words, when you create the record, this is the event time, right? But if you have the if you have the property set where you say, I want to be able to override this, then what the time that will be associated with it would be the time that is written in there would be the log append time when the broker writes it to the log. And you are absolutely correct. That log is not going to change. So when someone comes to process that log, they will just be using whatever processing is the processing time, but the log does not change. Does that sort of clarify it, Sharon? That makes sense?
Yes.
Okay, so the time does not change. The records written to the log are immutable, but just know that it's important to understand the two. One is the time the message is actually created. The second time is when it's actually appended to the log. And that time is, and the property you'll see, and you guys will see this a little bit later. I think we have it in your document as well. You'll see that we have this message timestamp type, and it can be either one or the other, right? And so you can say, I want to be create time, or nope, I want this to be log append time. And it's really important to understand that. Okay, because later on you'll see that. So now the reason I said that I want to hold on to it a little bit, because when we create the topic, we haven't talked about topic yet, right? If we create the topic and we configure the topic to say, look, we want this timestamp associated with it, then you will see that it will make a little bit different. But let's go through the topic And let's go through those concepts first, and then we'll see a little bit more about this. That way, everybody will be on the same page. Okay, so let's go on to this part. But for now, just know that this is your record or event or message. This is fine. And then Kafka would take your message, whatever it is, like Avro, Protobuf. I mean, you have different formats that we support in Kafka, because the brokers that we talked about before, they only understand bytes, ones and zeros, right? The bytes. So we have, you know, that objects can be serialized. So when people talk about serialization, objects have attributes, they have properties. We want to be able to serialize these objects and then be able to write them to disk, right? And so this is important. And then to do this, we have different frameworks that we can use. We can use Avro, Protobuf, JSON. So whether we're writing the data to disk or sending the data, most of serialization is sending it over the network, of course. But we want to be able to use these different frameworks to make this happen. So you can choose to use Avro, Protobuf, JSON, string, custom. Regardless of what you use, the idea is Kafka only understands the bytes. So then you got to have the deserializers to be able to understand. So this is why when you work with Kafka strings, you'll see that this concept of SERDI, right? Serializer, deserializer. So you'll be able to serialize the data and then deserialize it. So the moral of this story, before we get too deep, is to know that in Kafka only stores the bytes, right? And messages, all the messages are serialized before written to Kafka. So which makes it a little bit different, right? You say, well, how is this like a database? Can you guys tell me for example, how do I know the data format when it's just bytes in this case? If it's all bytes, how do I know the data format? Anyone?
The consumer and the producer must be coordinated in some way. If you use a well-recognized format, for example, you can use schema registry to, if you use Avro, to use schema registry to know the format of the data.
Yes, and that's the key thing is the schema. Schema becomes very important. And the schema becomes like your API, right? It's like your contract, but the schema is very important. So, and people often ask you this question. They go, well, in Kafka, do I have to use schema registry? The answer is no. You don't have to use a schema registry, but the problem is if you don't use a schema registry, you are increasing your overhead. So it's more effective to use the schema registry, which we'll talk about a little bit later. But we must know this, the schema is what's going to allow you to be able to, the consumer must be able to look at that schema to be able to understand the data format. So that's a very important part that knows the schema plays a very important part of all of this, okay? We'll see a lot of different serializers and deserializers as we go through the course. And then here's the Kafka commit log. So when we look at the commit log, remember, they say commit log, we're talking about what it means for messages to be committed. We haven't talked about that yet. But essentially, when you write to the broker will essentially store your message. So you're a producer, you send a message to the broker will take your message and store it to the disk, right? And on this disk, that's this log, the commit log. And just like you guys did in the class, right? These are the offsets beginning with 0. These are offsets. And notice it says old, because the first message that came in other words, the first user that writes into this log is going to come in here. Like the first number that came in was 9, right? 9, and then we have 4, 5, 11, 3, 17. So like 9, 4, 5, 11, 3, 17. And then let's go 3.74, 11. This one's 3.74. This is 11. And I think that was it. Okay, so example of people that wrote the data. So the messages are serially appended to the log, right? Those are offsets. And this is like the most recent message coming in. So if I were to type a number in chat right now, say number 20, okay, there's 20. So this is the most recent message coming in right here in the log, 20. And if this was the offsets right here, so this would be like, this is 11, so this will be offset 12. At offset 12, I have the number 20. I hope you're looking at this and going, yes, this is very basic, Hussein, simple, right? And that's my idea, is to keep it very simple. If this makes sense to you, the more complicated things we'll talk about will make sense. Any questions about this? Any questions? So if I ask you about the log, remember, this is not your regular log file. So the log looks like this. And when you look at this, you say, well, what are we looking at, right? Here are the producers. It's going to send messages to your brokers. And producers do not have to know about consumers. And consumers will come to consume the messages from the brokers. So that's why this is decoupled relationship. It's a decoupled relationship where producers do not have to know about consumers. Okay. And you could have many producers producing to Kafka, like each of you, just like you typed the number into chat, you were producing. And then consumers, you can have one consumer, or you could have multiple consumers in a group, and you can have multiple consumers group with different number of consumers in the group. It's up to you how you structure your, right? So a lot of different consumer groups, but they can all be consuming from the log at any point in the log. Does that make sense, ladies and gentlemen? Please let me know if that makes sense. Any limitation on number of offsets? Good question. You see, we use 64 bits, right, for the log. So it's 2 to the 64 power, which means you will never run out of offsets. What's more likely to happen, according to Eric's question, Eric says, any limitation to the number of offset in one log, or is it configurable? No. So by default, we use 64 bits, so 2 to the 64, which means this log file could grow forever to a quintillion. You never run out of offsets. But what's most likely to happen is, as you start to fill the log, what Kafka will do is when the log gets to 1 gigabyte in size, by default, it rolls over and then a new log begins. So your new log starts. So the file will grow to about 1 gigabyte in size by default, and then a rollover, then you have another segment begin. And we'll see more detail about this. Hopefully that answers your questions, Eric. So you will never run out of offsets because it's 64 bits that has been used. Okay. Does everybody feel comfortable with this concept? Remember, this is not a regular log file. This is like your append-only log data structure that is, as Sherwin mentioned, it's immutable, right? It's immutable, very important. That means once it's written into this log, you cannot change it. Now, of course, if I give you the root password, you can go to this file and edit it. But if you have the root password, you can change anything on the Linux system, but that's not something you want to do. In other words, the software itself will not allow you to edit this, right? So, and then now we get to this view of logical view, let's say, of Kafka topics, partitions, and segments. And we're right where I like to be. This is, when I teach this course, I always gauge the time, and then I will do a summary for you guys, and you'll see. Just look at the topics we're covering, and I want you to make sure you feel comfortable with it. We will get to a lot more detail, I promise you. Now, logical view of the topics, partitions, and segments. We haven't talked about what a topic is, but think of a topic as notice this is, say, Kafka cluster right here. A Kafka cluster is made up of brokers. That means these are like the physical Linux system, and I'm going to add the software. You remember the broker software on each of them, the service, and each system will be listening to port number 9092. Each of these broker will have a unique broker ID. They have this thing called the broker ID, and everyone must be unique. So let's say this could be broker ID 1, 101, 102, 103, 104. So every broker has a unique broker ID, but every broker listens to port number 9092, 9092, right? 9092. So with this in mind, you say, well, what is a topic? Well, think of a topic as a directory. For example, when you log onto a Linux system, you do ls, you can see the directory tree, and under the home directory, for example, let's see, for example, there'll be home Eric, home Martin. And then on a, let's say, Eric directory, Eric may have a directory for MP, for music. Maybe he puts all his music in one directory, and maybe he puts all his scripts in another directory. Maybe he puts all his pictures in another directory. Well, if you think about this, Eric didn't have to do this. Eric could say, look, I want just one directory, and that directory is called stuff under my home. And in my stuff, I'm going to put all my pictures, all my music, all my scripts, everything in one directory. Eric can do that if he wants. But in this case, think of this as a topic. So when you create a topic can hold, you can have a topic called stuff, but it can hold a whole bunch of different stuff, which doesn't give it a lot of organization. Or I could be more specific with the name of my topics. I can say this topic is called scripts, right? And just like I created a directory called scripts, and I put only my programs in here. I'd say directory called music, and I put only my music files, MP3s, MP4, because the format of these files are different from my script. So I don't want the I want to make it simple, and I can do that. So if you understood what I just said about a directory, then you know that, hey, well, when I create a directory, like in the Linux world, make directory X, and then I put a file in this directory, let's say file X, right? You know, this file doesn't really live on this directory, right? The file doesn't live, even though the file is, you create the file in this directory, the file is actually sitting somewhere on the hard drive, right? This file is sitting somewhere on the hard drive. What you have in this directory is just metadata, but that's part of the inode information, right? That knows how to get. Now in Kafka, we're not talking about directories, but the concept is pretty much the same. This directory is an abstraction. The actual data lives on the disk, and the inode knows how to get you there. In Kafka, we create a topic, and we create a topic that's relevant to what we're doing. Let's say we call the topic called payment topic. And this payment topic now this is like metadata. It's high-level abstraction like the directory. And this information will be kept in something called Zookeeper. That's like the metadata for this. But the actual data for this topic, just like in Linux, the actual data is on the disk. The actual data for your payment topic is now stored across the brokers. And we'll see how that's stored. We'll see why that's stored. Okay. Any questions about that before I move on? Using that analogy. So when someone says how many topics you can create any number of topics you want. A topic has partitions. The important thing is, just like I can say, I can make any directory in Linux, but how much data do I store in the directory? Because I may run out of space on the disk, right? While in Kafka, I can create any number of topics, but a topic has partitions, and partitions is what stores the data. So then I have to ask myself, well, how much data I'm storing? Because then there's a limitation in the number of partitions we want you. So Zookeeper is like, so in my analogy that I use, Zookeeper in a distributed environment is a collection of systems. Zookeeper is basically software. So in the Linux system, let's say I have a node, a container, whatever. I can install just the Java software on this system, this system, this system. And I call this Java, it's called Zookeeper.server, Zookeeper.server. I install the process on these systems, right? Their job is to store critical metadata for your entire cluster. That's what they do. So Zookeeper is a collection of, you typically do an odd number, like 3 or 5 or 7 systems, because they function together like quorum devices. And their job is to store metadata for the entire cluster. Everything that's going on in the cluster, they have like a little miniature directory tree. And each of these directories, what we call like nodes, they store about no more than like 1 megabyte of information. but they store metadata about everything that's going on in your cluster. And so the zookeepers are also a distributed system, right? So Kafka cluster currently relies on Zookeeper, but it's going away. As of 2.8, Apache Kafka 2.8, you no longer need to start Kafka with Zookeeper. It's what they call KIP 500. Of course, not all the features that Zookeeper currently does is implemented in KIP 500. So you probably still want to use Zookeeper until all of those features are there. But Zookeeper stores all kinds of critical information about your Kafka cluster. And they're very important to understand. In administration, we'll talk a little bit more about it, but just to know, do you guys have any questions about? So Zookeeper is the one that when you create a topic, I create a topic, the topic information is stored in Zookeeper, but the actual data will be here in Kafka on the disk, on the brokers, right? And you can create any topic, just like you do with directories. And the question says here, is Zookeeper responsible of coordinating the distributed nature of Kafka, like leader election? Zookeeper plays a role into it, but there's something else, and we'll talk about it a little bit more. One of the brokers in your Kafka cluster, let's say this one here, it can function as what's called the controller. Controller, sorry, controller. And the controller is the one that elects what's called the new leaders and the leaders, but that information has to be stored in Zookeeper. So that's why I say it plays a role. So there's one of the brokers called controller elects a leader, the leader, and all of that information is stored in Zookeeper. So Zookeeper plays the role of storing that information for the controller, so that all the brokers know who the controller is in the Kafka cluster. In a Kafka cluster, there can only be one controller at any given time. Okay. Everybody's okay so far? Okay. I will come back. I almost am at the point where I do my own little drawing. But this picture here, what this picture is trying to show you is an interesting picture, but it leaves out some detail that. So a topic has partitions. When you create a topic, let's say I create a topic called payments. And I say, I want this topic to have let's say two partitions. It may be 2, maybe 20, maybe 50. We'll talk about why you decide how many number. So if I say I want a topic to have 2 partitions and the topic is called payment, so then I'll have a topic called payment. And payment now has partition 0, and payment has partition 1. And let's say partition 0 is on broker 1, and partition 1 is there on broker 2. And let's say I have another broker here, broker 3, that doesn't have anything right now. I haven't talked about replication factor yet. So Kafka will automatically spread the partitions around. This is your payment topic. That information will be in Zookeeper, right? Zookeeper will store that information about the topic. And then how many partitions it has. And then partition 0 will be on this broker. Partition 1 will be on this broker. Does that high-level picture make sense? Please let me know if I need to clarify it any further. So a topic has partitions, and partitions store the log. So the actual log of the data will be stored here. Actual log will be under. We'll talk about this in more detail. So far, a topic has partitions, and partitions store the data. And then the question says here, this splitting, let's see. Yeah, so you basically are splitting the data across the brokers. And I'm not sure the second part is determined by controller. No, the way the data gets split up is determined by something different. And we're almost there. Unfortunately, sometimes when you go by the course material, it's sort of interesting format. It leaves a lot of questions, but I will summarize this for you because we're looking at a lunchtime coming up in 40 minutes. And I want to make sure I get you to the lab. So in the next 20 minutes, this will make a lot of sense before I introduce you to your lab environment. And then, yeah. So for now, I'm going to ask the question, do you feel comfortable with what a topic is? Everybody? Because remember, you will see a lot of definition in textbooks that say a topic is a queue, a topic is a message, a topic is a collection of messages. No, no, no. That can be very confusing. Just think about a topic like a high-level abstraction, just like a directory. In a Kafka cluster, I create one topic, or I can create a whole bunch of number of topics, however number of topics. And if you look at that example I used with Eric, instead of having one topic called stuff, where I just put all my data in, I may want to separate the user. I want to separate the user login info topic from the user payment topic, from the user balance topic, from the user profile topic. I want to have different information. Some customers will say, well, no, we are going to put all of this and just say user info. It's okay. It's up to them. They just have to have a schema that can manage that data. But I personally prefer to have my login info topic, my payment topic, my profile topic. I like to separate it. It makes it easier in my mind and easier to work with microservices too. But then we go on to this part. So a topic has partitions, and then partitions, notice it says segments here, because a given partition, like on this broker now, here's the log. So let's say this is partition 0 on this broker. When messages come into this file, it's going to continue to fill out this log file until it gets to about 1 gigabyte, or after 1 week, whichever one comes first. And then when this is full, Kafka say, oh, time to move that over. So it moves it over, and then a new log segment begins until it gets full. And then, oops, time to move it over again. And that's how you end up with different segments. So a given partition can have a lot of different segments. See, partition can have a lot of different segments. Does that make sense? Please let me know if you have any questions. This is where you ask the questions. So topic has partitions. Partitions store the data. The data is in the data, or your messages or events are in what's called the log, right? And the log will grow to a certain size and then rolls to a segment. It rolls to a different segment as it grows, right? 1 gigabyte or 1 week, whichever comes first. And then this is the picture. Someone has a question here. This is segments are created regardless of whether the message are consumed, right? Those segments are always, let's say if I have partition 0 and there's the segment size, the default says when you get to 1 gigabyte or 1 week. So there's a property called the roll millisecond. So over time, if that time frame is met, it can roll over into a segment. So in other words, it can be time-based, but the default is 1 gigabyte or 1 week before it rolls over into a second segment. But there's different properties to control. Like if you want to play around with this and you want it to roll over in 5 minutes, you can change the time. There's like properties like the segment bytes to control the size of the segments, or roll milliseconds to control when that roll happens. So yeah, there's properties to control it, but the default is 1 gigabyte or 1 week. And then Cetric says, is any partition of the topic able to retrieve the entire message? The entire message is typically written to one. So let's say if I have here's my partition 0, and partition 0 has the log file in here like this. This is offset 0, 1, 2, 3, and more offsets. And then here's the message, a given message coming in like this. This is message. So this partition gets the entire message here. And in Kafka, we want this message size to be less than about 1 megabyte. Unless if you're in our Confluent cloud, we optimize it. I think we can hold up to 8 megabytes now, maybe even bigger in Confluent cloud, because we optimize it from 2 to 8. And if you guys are curious, you could just ask, but we optimize it. But in Kafka, the message size should be typically about 1 megabyte. So a given message, this may be just bytes, or it could be 1K, 2K, 3K, 4K. 10K, 100K, but we want you to keep it less than a megabyte because Kafka prefers to smaller messages. So each of those are records or messages. And we'll talk about batching and all these things coming up in just a little bit. Okay. So it's any partition of a topic able to retrieve the entire message. So, so the partition should have, a given partition should have given message, but in other words, if you say all the data, no, the data will be spread out. So in other words, if I have a whole bunch of data here that I produced to Kafka, some of it will be on partition 0, some of it will be on partition 1, some of it may be on another partition 2, and we'll see how it gets there. The data will be spread out across the different brokers in those partitions. Okay. Promise to summarize this for you guys coming up in just a second. So a given broker, like this is broker 2, broker 101, broker 103, broker 104. Each of these brokers, notice it has the green. It says the green here is the partition 0. So partition 0, and then here's partition 1, and here's partition 2. So this topic, the green one, topic A, has these 3 partitions, and notice that Kafka spreads them across the broker, right? So partitions are spread across the broker. See, partition 0, partition 1, partition 2. It's spread across the broker. And then each partition has its given segments. Okay? And then now we get to this concept of log retention. So we don't want the logs to grow forever. So after some time, we need to clean up the log. When you create a topic, you can specify the cleanup policy for the topic. You can say, look, I want to keep this for maybe the default will be delete. That means the log will be deleted. And the default, again, is like when you get to 1 week. But I can say, I want to keep this for a longer time. So I can change the retention policy, right? The default is delete, but you can change the retention policy. You can also say, I want this to be compact. And if you say compact, then we'll see what compact means. But it says for given key, I want only the latest value associated with the different key. So you can have delete and compact. And then again, when we look at this picture, oops, sorry, let me just click on my lightsaber just went off. It said delete segments when they get old. Too old means the message is older than the retention millisecond, which is the default is 7 days. Okay. And then when they delete, they say delete the oldest segment when partitions get too large. This is retention bytes. By default, it's unlimited, but you can say, look, when it gets too, so you can change these properties at any time, right? But when you combine the delete, there's also this thing called compaction. So compaction says, look, for a given key, I want only the latest value for a given key, right? So for a given key, I want only the latest value. And then what do I do for compaction? So when you're doing real-time table lookups, joins, doing stream processing, they're very useful, right? You want to get the latest state after failure of an in-memory application, or you want to do CDC, database change, what they call CDC, change data capture from the database. So the use cases that can be very useful to use compacted topic in that case. So how does compaction work? So this is the log file that is on the disk that has all of these like key value pairs. So here's the customer ID, and this value is all the information about the customer. They're just like a V1. Remember, that could be a whole bunch. It could be a kilobyte, 2 kilobytes, 10 kilobytes, but there's always a key. So assuming that this is the first record in the log, and then here's the latest record in the log. And as you can see here, so this key K1 appears here and also appears later on here. So when compaction occurs, it scans the logs, the existing log segments. Remember, those are log segments that are on the system that I've already rolled over. So Kafka will look at these log segments to see, like, hey, when did we just do compaction? And then it will say, okay, I'm going to build some kind of in-memory map for every key, like here's key 1, and I want to find the latest value for key 1. It scans all the segments that I've rolled over. And then it says, okay, the most recent key 1 I see has a value of V10. So after compaction, this is it. And then it will scan the logs, scan all the segments also, scan the segments for like key 3, and say that key 3 has to be V17. So for K3, the latest value is V17. So that's why after compaction, it looks like this, you see. So you have the time, the key, the value. So for given time, they're all here. So compacted logs is for given key, giving the most recent value associated with that key. Okay. Let's think about this from a developer perspective. So let's say you have the log file and you have payments coming in. Here's a customer ID. I'll say customer ID 1, and the customer is in New York. And then the same customer ID, well, this is ID 2. Customer ID 2 is in California. And then customer ID 1 is a tracking system, like a delivery system. Tracking system, delivery system, customer ID 1 is now shows up that customer ID 1 has a record that shows is in Ohio. And then customer ID 2 shows up again, and it's in New York City. Well, if you were to do a compaction to show this compaction topic, after compaction of records that look like this, you will have just the customer ID 1, and the most recent occurrence in the log will be Ohio. And the last one here, customer ID 2, will have New York City. So this is what a compacted log would look like. Does that make sense? For given key, you want only the most recent value associated with it. And if you understand this, you'll see when we get to the streams section, it's going to make a lot of sense to you.
Oh, hi, Hussein. I have a question.
Yes. Yep. Mm-hmm.
Yeah, this is Gang here. So I just want to ask, right, the compacted log, is it being represented by another topic, or does it mean that when a new consumer were to retrieve the topic, he will only get the latest record?
Good question. So it's when you create a topic, let's say we have that payments topic, right? And I set the policy, I say I want this to be compact.
Yeah.
And let's say compact and delete. Then that means I know I will have a lot of segments in the partitions of this payment topic, but then at some point, instead of deleting them all away right away, Kafka will go and look for all the different keys, build that in-memory map, and give me only the latest value for given key, and then I have a new log in that topic. So you still have the payments topic, but then now, just like you said, you have the latest record, latest value for a given key. But the one problem you have to be careful for is that it's not 100% guaranteed that the consumer will get only the latest value. Let me tell you why. Because compaction never affects the active, what's called the active segment. In other words, this is the segment that is currently getting the messages coming in. It has not rolled over yet, right? And after about once this gets to a certain size, like 1 gigabyte or 1 week, then it's going to roll over into this is a segment, a rollover. But if it's an active segment, what if I still have key 1 and value 1 and key 1 and value 1? I may have key 1 occurring several times in this log file, but this one has not undergo compaction. And then this one just happened 5 minutes ago. So now let's say every 5 minutes, the thread runs to look for compaction, but it hasn't been 5 minutes yet. So the last compaction occurred 5 minutes ago. And then now it's been about 2 minutes, and then this log rolls over. The log rolls over, and in this log, I have lots of key 1, value 1, key 1, value 1, key 1, value 1. So as a consumer coming in, the consumer hasn't gone through the compaction process hasn't happened yet. It has like maybe 3 minutes to go. So that means I will have multiple of the key 1 and value 1. So you have to be aware of that. But yes.
I see.
After
Understand.
compaction runs, you're okay.
I see. So just one quick question. Can you just remind me quickly what are the parameters that affect the frequency of the compaction again?
Good question. So there's a background thread that runs by default. I believe it's every 5 minutes, and you can adjust that. But the compaction itself, it looks to see when about 50% of the message is, in other words, has not undergo undergone compaction. When about 50% is considered to be dirty, then it wants to do compaction. But what really affects it from a developer perspective, I think this is the question that you really want to know, is let's say I create a topic and I say, this is going to be a compacted topic. And then I know now I can produce messages to this topic, no problem, but a compaction will occur, blah, 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 blah. I know all of those things. But when compaction runs, I notice not much changes happen. I use resources to do compaction, but then I don't see much results. Then why? And this is the part that I think is critical based on your question. As a producer, as a developer, when you write producers, if you have a high cardinality of keys, that means let's say a lot of the keys are different, then you will not have reoccurring keys in the log. And if the key is not reoccurring because all the keys are different, key 1, K2, K3, then compaction is going to run and use resources, but they won't have a really good effect because you have too many unique keys. So from a developer perspective, that is the most important thing to understand, that you must produce data with keys for compaction to be of value to you. And you must also, you cannot have a high cardinality of keys. They can be all different because compaction is not going to help you very much. And I think those are two of the really important, and then the other ones, just adjusting how frequently the compaction process runs. But those are the really, really important parts to be aware of.
I see. Thank you. Thanks for the clarification.
Yeah, you're welcome. Everybody's doing okay? Okay, I hope so. Let's go on to replication. So replication, what is replication? And then after this, I get to do my drawing, and then I'll get you into the lab, and then we'll have a first lab. And then when we come back, I would try to talk less and you'll see there's a lot of information to go into. Once you see the logs, you will see why. But remember, there are a lot of you that are new to this. So I found this method really works well when we have people who are new to it. So for those of you who are a little bit more experienced, please bear with me, but we will get there together, right? Replication of partitions. So if I have a payments topic, I create a topic called payment, and I say I want 2 partitions. So Kafka will say, okay, here's partition 0, here's partition 1. And then this one could be on one broker, and there's another broker. And let's say I have 4 brokers in my cluster, right? Broker 1, broker 2, broker 3, broker 4. So now my topic has 2 partitions. But the problem with this is, as you guys know, if I lose this broker, then I have no way to access partition 0. That means all the data in partition 0 is no longer available to me, right? Because it's a single point of failure. So when you create a topic, you can specify the topic, but you can say, look, I want the replication factor. And you can say, I want the replication factor to be 3. In production environments, we typically do 3. And then what does that really mean? It says for each partition, it must occur exactly 3 times, okay? So in this case, P0 is here. That means I need to have 2 more P0. So I'll change the color right here. So let's say partition 0 is here. Oops, there we go. Here's partition 0. I need 2 more instances of partition 0 to have a total of 3. That's replication factor 3. So Kafka will put like partition 0 on this system, and let's say partition 0 on this system. See, exactly 3 copies of partition 0. So now if broker 2 dies, no problem, because I have broker 4 and broker 1 that has that. Everybody with me on this one? Please let me know if you have any questions about that. So if a broker dies, you still have access to the other 2. Then for P1, Kafka will say, okay, we need 2 more copies. So let's put a P1 here, and let's put a P1 here. It will never put 2 partitions on the same system. So now, this is what we have. Kafka spreads out the partitions across the system. So if we look at this carefully, this is like a chart now. Think of it as broker 1, broker 2, broker 3, broker 4, and Kafka will say, okay, now that we know those brokers are here, okay, we have partition 0, and we have partition 1. Sorry about that. Let me do this, redo. So let me know if you have any questions about what I'm about to do at all. So Kafka needs to say, look, when you have to send data to partition 0, we want to know who the leader broker is. In other words, there's this concept of leadership. So for partition 0, we must have a leader. And for partition 1, we must have a leader. So this is partition 0. And this is partition 1. So it says, look, let's say we would just appoint. So for example, partition 0, we'll see broker 1. So broker 1 is the leader for partition 0. We'll just make broker 1 the leader. We'll talk more about it in just a second. So what does that mean? Well, what other systems look at the diagram and tell me what other system has partition 0. Can you guys please humor me? Please work with me. What other system has partition 0? Is anyone still there? Yep, 2 and 3 has partition 0. So that means for this, broker 2 will be a follower for 0. And I'm sorry, you said 2 and 4, right? Yeah, 2 and 4, sorry. And broker 4 will be a follower for 0. So you see? So for partition 0, broker 2 is a follower and broker 4 is a follower. And then if we look at the same thing for partition 1, let's just assume that partition 1, we will say for partition 1, broker 3 is the leader. So we'll make broker 3 the leader for partition 1. So we'll say the leader is here, broker 3. Then it must have, the rest will be followers. And then in that case, broker 2 and broker 4 will be a follower. So broker 2 will be a follower and broker 4 will be a follower. And you say, well, what does this really mean, Hussein? Because in Kafka, whenever you are producing to a Kafka cluster, where I have brokers here, and brokers are stored in the partitions, all producers and all consumers, they communicate only with the broker that is the leader. They communicate with the leader broker. In other words, the broker that is the leader for partitions. So look at this chart real carefully, and I'll show you this. If you have data to send to partition 0, my question to you, what broker do you think all producer requests will go to if you're sending it to partition 0? I haven't told you how the data would get to partition 0 yet, but let's just say that I'm sending data to my Kafka cluster and the data needs to go to this payment topics, and this payment topics has these 2 partitions, 0 and 1, with a replication factor of 3, which is the picture we were looking at right there. In this case, what broker will get, if the data is going to partition 0, what broker in this picture will get the request? Can you guys tell me? Broker 1, that is correct. And if I tell you the data is going to partition 1, if I say going to partition 1 and I say what broker is going to get the request, you know it is broker 3, because broker 3 is the leader for partition 1. Then you say, well, then what is the job of the followers? Well, soon as the leader get it, what was the question? So I thought we have P1 because P0 already full. No. Good question, but no. So when you write data, we'll see how it goes. If the broker has 2 partitions, let's say partition A and let's say partition 0 and 1. So when I send data to this partition, we'll see this coming up. I will do a hash of my key modulo number of partitions. In other words, some of my records will come here, some of my records will come here, some will come here, some will come here. And it will be distributed across the brokers. Okay, So whenever my brokers are going in, processing is in parallel, correct. So when you produce the data, your data is written across multiple partitions. And when you process in parallel. But does this picture help you understand this? Yes. Okay, so what we need to do now is keep this in mind. Soon as the leader gets the data, the follower will fetch the data right away from the leader. Now, in this picture, notice that imagine that you're in a zone, East Coast, right? Yeah, East Coast and West, I'll just do it this way, West. If a consumer is here on the West, it would take a very long time to come here to the East to get the data. So we have this ability for consumer to fetch from the follower. So if there's a follower in the West, the consumer can fetch from follower. And that was added as of Kafka 2.4, where consumers can fetch from a follower. So the follower is closer to where the consumer is, and the consumer will fetch from the follower. Okay? But what does that mean? When you produce data, you send the data to, so here's my data to be sent to the Kafka cluster. When I produce the data comes in. Let's say if this guy's the leader, then as soon as this guy gets it, and let's say this is a follower, the follower has to fetch it from this system right away. Follower comes and copy it right away. So for example, I see. I yeah, so I got it. So in this case, if the leader gets the data, the follower comes and fetches the data right away from the leader because the follower has to write it into its log. And so that way, if the leader broker dies, then one of these followers will become the new leader. And then all the producers and consumers will come to that new follower, right? So replication is for durability. You replicate the data so that your cluster is durable. So if a broker dies, you don't lose your data. You still connect to another to another broker, okay? And then this is what they're saying, the leader failover. So leader can fail, if a leader fails, right? Another broker will be elected to be the new leader. And then you will just continue to connect to the new leader, okay? Who nominates the new leader? That's the controller. It's the job of, so one of the brokers in the cluster, one of the brokers, let's say broker 4, for example, the broker is multi-threaded. So one of these brokers functioning, one of these threads function as a controller is the one that will, so the broker connects to the zookeeper. And remember, a zookeeper is typically like a 3-node, a 5-node collection of systems. And the first broker that is able to write under the zookeeper directory, like what they call the controller directory, it becomes the new controller. And this controller is the one that elects the new leader. So if a broker fails, the controller elects the new leader, okay? And then it stores that information in Zookeeper. So if the controller itself dies, then one of the other brokers in the cluster, the first one that comes and read this information in Zookeeper, becomes the new controller. There must always be one, like the Highlander. If you like sci-fi movies, remember Highlander? There can be only one. If you don't know the Highlander movie, you have to now watch it because it will help you learn Kafka. There's can be only one controller in the Kafka cluster, okay? And then now, remember we talked about load balancing? If I have only one partition, so if I have a payments topic, here's my payment topic, and I have only one partition, partition 0, then that is going to live on only one broker. Let's say broker 1. Even if I have 3 brokers or 4 brokers, so let's say broker 2, broker 3. Because I have only one partition, that partition lives here. Even if I replicate this partition, then replication factor 3, that means there'll be a copy here and a copy here. But remember, all your producer requests and all your consumer requests has to go only to the leader. So you go only to the leader. So what that does is, if you have lots of producers and consumers writing to a topic with one partition, then that creates a hotspot, right? So you have to be aware of that. Okay. But if I want this to, if I spread my partitions out, like you see here, this is a broker, 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 then every broker has a leader. I mean, this one, see the blue? So this one, the blue. So there's no hotspots because the leadership is spread across the brokers. So your consumers and producers will go to these different brokers. Does that make sense, guys? Please let me know if you have any questions for that. So essentially, if you have more partitions, you can spread out the leadership across your brokers, and it's more balanced kind of load. Okay. Question says, able to share how a failed broker recovers and to be in sync with the rest of the broker? Yes, actually, I can talk about that. And the whole concept is when a broker, so there's different things if the broker fails versus if the broker just maybe gets a little bit slow, right? So there's this concept in Kafka, here's a broker, here's a broker, here's a broker. Let's say this is broker 101, this is 102, this is 103. If they're in sync, that means, let's say this is leader, follower, follower. What that means, as soon as the leader gets the message, the follower has up to 30 seconds to copy it from the leader. 30 seconds to copy it from the leader. So within that 30 seconds, if the follower can copy it from the leader, then the follower is what's called in sync, right? So let's say the in sync will have 101, 102, 103. They're all in sync because as soon as they get the message comes to the leader, the followers copy it right away and they're in sync. But if this follower, for whatever reason, maybe the network or garbage collection, whatever, is a little bit slow, let's say maybe it's 55 seconds behind, then it's considered to be out of sync. And what happens is then the list of in sync replicas will look just like this: 101, 102, and now 103 is a little bit too slow. So what that means is, if let's say 101 fails, 101 is the leader here in this picture. If 101 dies, then only 102, for example, has the ability to become the new, because a broker that is out of sync, if you're out of sync, you are not eligible to become a new leader. So this is considered to be the in-sync replicas. All the brokers, all the leaders and followers that are within that 30 seconds time frame, they're in sync. If they fall out of that time, they're out of sync and they're not eligible to become a leader. But you can also decide, because when you are asking a broker for something, you say, look, how many brokers are allowed to answer? How many brokers must be up and responding to answer my request? This is a property called min in-sync replica. And actually, I think we'll see it a little bit later. I won't go too much into that. I want to make sure I get you guys to lunch by, let's see, I know it's 8:30 Singapore time. We're almost to 11. So by 11:30, I want to get you into lunch. Okay, if that's okay. So is 11:30 okay for your lunchtime? Everybody? Okay, awesome. Okay, I'm also okay with 12, but it's just that 11:30 is easier break. Then, yeah, so what I will do is I want to get you guys to the lab, and then we will give you lunch and lab. So which means you get 1 hour for lunch, and then you will get maybe an extra 30 minutes for break. And then we will have, so you'll have like maybe an hour and 30 minutes for that combines lunch and lab. So from 11:30, 12, 1, then we'll return at 1 o'clock. And someone says, can we have, yes, absolutely. So my plan is to introduce you guys to the labs before the break. So you have all the slides, you have the environment, I'll show you how to access it. And you guys can, from that point on, it's like wildfire. You will just do whatever you want. Okay. So let me come to this part. And now this comes to this part where it says hands-on. But before I do this, right, this is the point where I mentioned before, I like to do this for every class. I've gone through the slides and it sounds okay, but I want to step back for a second and just do a little drawing for you here in my Kafka cluster, just with some diagram, just so you can understand a little bit, okay? And then we'll go to the lab, and then you guys I'll show you the lab. So just a recap of what we covered in this chapter, okay? I want to do a recap. Very important to do the recap for this early stage. And I'm going to ask you questions as we're doing this recap, okay? And you can let me know if you're okay or not. So number one, a Kafka cluster is made up of brokers, and we know that, right? Let's say I have 4 brokers. Every broker has storage attached. We'll just pretend this is your physical setup in your environment, okay? These are storage. You download the software to each system. But remember, the bundle has all the different components. It has the connectors, it has the KSQL DB, it has the REST proxy, has everything. What we need to do is turn on the broker software, the one that makes it the broker, right? We turn on the Kafka service that makes it a broker. So let's just, each of these brokers, this is like broker 1, broker 2, broker 3, broker 4. Every single broker will be listening to port number 9092, right? Every single broker. Now, from a systems perspective, each of these hard drive here, in Linux world, these are like dev, SDA. Let's say the one drive, and then the second disk would be like the dev, SDB. So most administrators would take the drive like this and put one partition on the disk, and then that becomes like the dev, SDA1. And then this one will do the same thing to this, put one partition on it, and then it becomes this dev, SDB1. That's for this system. The same thing will be done on this system and this system and this system. Then I need to now have a mount point for these disks drive. I have to put a file system on it first. So I can do something like this, nkfs.xfs, put a file system on this dev, SDA1. Now there's a file system on this. This is a Linux file system, and I'm putting it XFS on it. But then now I need a mount point. So I now need to make a directory in Kafka. I'm going to say make directory. Let's go with it. We'll say, for example, on the root, we'll call it iras-kafka. Or let's just say IRASK to say Iris Kafka. Okay, let me clean this up a little. Just say IRASK. We'll just say that the Iris Kafka directory. We'll just make this just for, you could call it whatever you want, but we're making a mount point, right, under the root directory called IRISK. That's the name of the mount point. Now, when we install the software in Kafka, just like most other software you put on a Linux system, under the etc directory, a lot of administration files will be put there. So there will be a Kafka directory. And under this Kafka directory, there will be a file called server.properties. Right? And in the server.properties file, there's a whole bunch of default parameters for the broker. Remember, this is for the broker config. Whole bunch of different configuration in this file. One of the things you'll see is something called log.dirs. It says, look, when the data is coming in, what directory do we write it to? In this case, you would tell it to say, look, write it to IRISK. Like Iris, maybe there's Iris1, and maybe you also have another one, IRISK2. So you put a comma separated list, IRISK2. You put the 1 and 2 in this directory. So far, any questions? This is strictly from a systems perspective, what has to happen before you even start to work with Kafka. You set up the Linux system, you put them all together in a network on the scene, VLAN or whatever, or imagine if you're in the cloud, they could be in different availability zones or wherever. We'll look at some of those. But pretend right now you're on just in your local network, or you have them connected over the network. You install the software on each one. Every single system has the same server.properties file that comes with the broker software. Inside of the file, there's one line that says log there. It says, where do you want to write the data when it comes into the system? Where do you want me to put the data that comes into the system? And you say, look, here's the mount point. So iris 1, iris 2. Now, questions say you can assign multiple directories to log theirs for scalability. In other words, what it is this. It's not so much for scalability, but what you're doing is you have your disk drives here in this storage that your broker is using, and you want to tell Kafka where's the mount point, because every disk needs a mount point. And now, because I'm using separate drives and maybe I'm not using RAID, then each disk is an individual spindle, and each disk needs a mount point. So I need to put a file system on the disk and then give it a mount point. So in this case, I will, after I make this directory, I will have to mount the disk, like say mount, like /dev SDA1 to like this IRISK1, and then I will have to mount /dev SDB SDB1 to slash like iris2. Every disk will have to be mounted to its mount point. And then the final point to all of this is you will add the entry, add to the etc fstab, FSTAB. Because in Linux world, when you reboot the system, if you don't have the entry into this file, the entry will be lost. Now you may be wondering, this is a developer class. Why is this necessary to know this? I was at a customer site, big customer, I won't say the name, big consulting firm in Florida. And this was years ago. And it was Hadoop. We're working with Spark actually, but they had changed the volume. So in the middle of the class, all the students started, they were all focused around one student in the class, and they weren't paying attention to me anymore. So I said, okay, well, guys, hey, I think it's a good time for a break. And then everybody's, oh, sorry, we have an issue going on in production. And so we took a break. And when I walked over to them, I said, oh, what's going on? They said, oh, there's some issues going on with the volume, and they didn't know what happened. Things are failing. And then because the production had changed their volume, and I just asked one question. I'm like, oh, where was it mounted before? And then some of the developers looked at me and go, I don't know. How do you? I said, just look at the fstab file, because this fstab file is a permanent entry that does not go away. If you have a mount on the system, regardless of whether it's a RAID volume or any kind of volume, the entry needs to be in this file so that when the system reboots, this is during the boot process, it will say, oh, I need to go find this disk and I need to mount it to this mount point. That's what it does during the boot process. So when you put it in the fstab file, you tell it about the disk and the mount point, like device to mount and mount point. And so during the boot process, Linux will go find it, the disk, and then mount it to the mount point. So all they had to do, so when the guy looked in the fstab file, he saw that the previous volume where it was mounted, and then they were able to make a few calls and just change it. And then boom, all that issue went away. And I'm not saying that to say, oh yeah, I solved the problem. But sometimes if you're working in an environment, you need to understand a little bit of the underlying architecture. You don't have to be an administrator. You don't have to be that. You can focus. And this is the good thing about our cloud. So if you come to Confluent Cloud, we take care of all of this kind of stuff for you. You don't have to worry about any of this thing I'm talking about, right? Confluent Cloud abstracts all of this away from you. But if you're, after this class, if you have to do this in your own environment, or if you are working as a consultant someday, you need to understand this because maybe the person has a RAID volume. So I'm saying mount each disk to its mount point, but what if the person say, hey, Hussein, can I use a RAID 10? What if I have, this is my storage, and I put here 1, 2, 3, I have 4 disks. I want to use a RAID 10. In that case, how many mount points do I need up here? Well, in that case, you need only one mount point. You can just make one mount point, call it whatever, let's say Kafka data. And then what I do is RAID 10 means when you strike the data here, you mirror the data to other disk. So if I write like H here, then I write H here. If I write ELL here, O, then I write ELLO here. So there's every stripe is mirrored to another disk. So if I lose this disk, I still have the data here. If I lose this disk, I still have the data here. So when you have a RAID 10 volume, this gets a name like, let's call it vol 1. Then what I need to do is mount this vol 1 to this mount point. So in this case, I'm mounting only one thing to the mount point, and I mount the entire volume here. So if you're using a RAID 10 in Kafka, you need to understand this. If it's a RAID 10, I don't need multiple mount points. I just need, because this will be a stripe, then you mirror the stripe. I stripe, write data, then I mirror that data to another disk. That's what a RAID 10 is. In which case, this entire thing will be given a name, like volume 1, or whatever you call it. And then I will be able to mount that volume to one directory here. So whenever you tell Kafka now, in Kafka, instead of having these two directories, I'll have just a log dir to say, look, write to this Kafka data. And whenever messages come into the broker, to any of the broker, it will send a message to Kafka data, which means it will send a message to this volume. Okay? Is everybody okay with that? Because I'm going to take this to the next step now. And then we will almost do the lab. Yes, excellent. Thank you very much. Okay, so very important points. Again, not so much from a developer perspective, but very important to know. So if I clear this picture up, let's do this. Almost ready for you. The lab part goes very easy. It's very, very simple. So we know that the server.properties file is very important for you to be able to configure your broker software. But let's look at how the data comes into Kafka now. Okay, this is the last part to this, just to finish it up. And there's a command you'll see to create a topic in Kafka. We call the Kafka topics. So there's a command called Kafka topics to create topics, right? Kafka topics. I can use option like -- create. When you say create, you will want the topic name. So let's say I have a topic name. I want to say the topic name. The topic is called, for example, let's say robo, like for robot info, right? Or just say robo for robot. And then I can say I want the replication factor. I'll just abbreviate it right now. Replication factor equals, let's say, equals 3. And I want the partitions to be equal to 2. So we'll see this command working, but let's just say I do this architecture right here. So here's my broker. We'll keep this picture very simple. This is now my Kafka cluster. And remember, each Kafka cluster has its own storage, like we saw in the pictures before. But then now, assuming that every single one of these systems have a top-level directory called IRASK. This system also has a top-level directory, IRASK. IRASK, okay? Because when we set up Kafka in a server.properties file, remember that property in the etc Kafka directory, right? This is server.properties file, right? And inside of that directory, we'll say the log.dirs. We'll say, look, write to this IRASK. And we can make an assumption that we have the volume like in array 10. That means there'll be 1. So now, when we run this command to create this topic with 3 partitions, this is what's going to happen. You have the topic called robo, and it's going to have partition 0, 1, because I have two partitions, right? Two partitions, actually. So that means I will end up having a partition 0, and let's say partition 1. Okay? And let's just say this is the broker, broker 1, broker 2, broker 3, and broker 4. Okay, so now with that in mind, we have partition 0 and partition 1. So I'm going to make this a different color here by changing this blue, and we're almost done with this. Okay, almost done. So this is partition 0, partition 1. Then replication factor, I'll add a little bit later. But now on this system, under this iris, there will be a directory, which will be called robo-0. And then under this system, there will be a directory that will be under here, this one, that will be called, so there will be a directory called robo-1. And in this system, 0, there will be a whole bunch of files, but the file we're really interested in has a whole bunch of zeros. It's like 20 zeros, and it ends with a .log. And this is the actual log data file. And this one also has a whole bunch of files, but it has one called, again, same thing. There's like 20 zeros .log. And this is the file when we say log file 0, 1, 2, 3. This is what we're talking about. So look at this picture now and see if you have any questions for this. So when a message comes into Kafka, because we're going to look at this, when you're producing message, we'll see that the producer will do hash of the key modulo number of partitions to determine where to go. So in this case, the number of partitions in this topic is 2. So it's like take whatever the key is. Let's say if the customer 101, it would do the hash of this and then modulo 2. So the answer will either go, the result will either go to 0 or will go to 1. If another customer ID comes in, customer 105, right? That will go either to 0 or 1. So whenever you see customer 101, if it went to 0 before, it will also come to 0 again. Customer 105, for example, if it comes to 1, then it will also come to 1 again. So this is how, when your message comes in, if it's coming to partition 0, then this broker will eventually write it to this robo-0 directory into this log file. So this morning, when you wrote your answers into chat, it'll be like the 9, whatever numbers you wrote will be coming into this like this. And if the message were to come into partition 1, then it will come to broker 3, and then it will end up on this broker robo-1 directory, and it will be in this log file. Any questions about that? Because if you understand this, then you're good to go.
Hello, I'm Martin here. A little bit confused on the indexing and the log file, because it is the same topic right now, and then we were talking about offsets and whatnot. So if the log file repeats from 0 under log 1, then how would they know whether, how would the consumers know where should they continue picking up the messages?
Good question. So this log file will go, this one, let's say, yeah, this log file starts at, it always starts 0, then this goes 0, right? Because that's the first log file. But now in this partition, I can have many segments. So when this rolls over, right? In this directory, I will have another segment. So now this one will be the 0, but the new segment now will be like, let's say this is 000193885, some .log. But in other words, the name of the log file is the file that represents the messages that from the first message it contains. So if this one ends here on 9359, like 93 million something, then the next file will start like 93 million one or whatever that the next file starts from the next higher number up. That's the name of the file. And then all the messages will come into that file, but it's still in the same partition. Every partition has this, always begins with 0 and then rolls over. And then the next log file starts with whatever the last offset is here. That is the name of the next file for this partition. Does that make sense? Sorry, it's a little messy space.
But it adds an extra point of knowing that within the same partition itself, the running number keeps ongoing. But from one level above, right? Let's say when I'm trying to consume a message, how do I know I am taking the latest one, given that now that I have 2 partitions?
Because you don't have to worry about it. I'll tell you why, because we're not there yet, but there's this thing, a consumer always process. So let's say this is the log file, right? And here's the offsets. And this is all the mess, 1, 2, 3. And let's say down here, this is like 1,965,000. It's a huge number here. But if the consumer is here, the consumer, regardless of where the consumer is, it always stores this information into something called the underscore consumer offset topic. There's a consumer offset topic. In other words, it's a special topic in Kafka where every consumer keeps track of where they are, and we'll see this coming up later. So the short answer for you right now is to know that a consumer always keeps track of its offsets, like where it is. And there's a tuple of information that is written to the offset topic. It says, hey, I'm a consumer. I'm in group H1C, and I'm managed by this group coordinator. We'll see that coming up a little bit later. And here is the robo topic that I'm consuming from. And here is the partition number, partition 0. And this is the offset that I want to commit, because if another consumer comes in, it needs to start from this offset 9,056,207. So it always keeps track of where it is. Yeah, but we'll see more of that detail. Oh yeah, another question. Sorry, go ahead, King.
Yep. Hi, I think this is just a extension to Martin's question. So maybe let's say a scenario where it's a fresh new consumer. So using this robo topic, so let's say it is a fresh consumer with a fresh consumer group, and I want to read the topic from robo. So I can either start from robo from partition 0 offset 0 or partition 1 offset 0. So how does the consumer actually choose which one to read first?
Yeah. So what happens is the consumers store the valid offset, and actually, unfortunately, we still have a lot to cover before we get there. But you keep track of where you are. So if you go away, another consumer will come and start from where you left off. So they always stores that in the offset topic. But in the API, it says, look, what do we do if we don't have a valid offset? Like if I can find my offset in this topic, then I have a choice to say start from the beginning of the log or start from the end of log if I want to, or maybe throw in an exception or do something else. But so that's what happens if you don't have a valid offset. But typically the consumer will commit the offset. So you start with a valid offset, and you can choose to start where you want if you don't have a valid offset. But then also in the API, it allows you to seek to any point in the log if you want to. You know, like when you're writing a C program and you want to seek to a different position in the file. So in Kafka, we have that ability to seek to any point in the log as well. But the offset part, we'll see, we have a whole bunch of stuff to talk about that. So for now, the key important thing, yeah, thank you. You're welcome. The key important thing that I would say, if you, from this, I know I've talked a lot, but the important part is, I'm going to introduce you guys to the lab before we go to lunch. But the important part is this: understand that when you write to Kafka, you're producing to the brokers. Brokers have those partitions, and partitions have the logs. And the logs will grow in size, like 1 gigabyte, one grows up to 1 gigabyte, then it rolls over. And you'll see some of the information we're talking about is actually going to come back to you. You may think I'm talking a lot, but I like to introduce it this way because we will see a little bit more of this in the next chapter as well. But this next chapter will be so much easier for you to understand when we start talking about these things. And it's not so much a operations administration course. So this is like as much as, we have the time for it to get you into the material, but the important thing is to understand from this, hey, I know what a topic is. So topic is an abstraction, like a directory. Topic has partitions. Partitions is what's going to store the information in those logs. So partitions have the logs. The logs are spread out across the different brokers, right? And then regardless of whether you're a producer or you're a consumer, you only communicate with the leader. If the leader dies, a follower can become the new leader. And we'll see some of this in the next chapter. But this is something I just wanted to show you, because when you're looking in the lab and you're playing with the lab, you can actually go and examine this system and look at the directory and see all the files. There will be like an index file, a timestamp. Later on, you may see snapshots, stuff like that. But the important thing in every partition is the log file. That's the immutable record. You cannot alter this log. Every message is appended to it serially. So when a consumer comes to process this log, the consumer will store the offset. And we haven't even got to consumers yet. So you'll see the consumers coming up later. So just one last recap. Understand brokers, topics, partitions, logs, replication. Replication is for durability. We replicate the data. This is just showing you one partition, but we know that we want to do replication factor 3. So we'll put another P0, another P0, another P1, another P1. That means exactly 3 instances of the given partition. And then that way, if a particular broker fails, we will talk about it. I'm sorry, I know someone asked about broker failure. I will talk about it a little bit more when we come back on another time. I try to incorporate it into the lecture. But a broker can catch up at any point. You can put a new broker in the cluster, give the broker the same broker ID, and it will try to fetch the data. And in the new Confluent platform, we have this concept of what they call self-balancing cluster, which means this is a new feature. If you put a broker into the cluster, Confluent platform enterprise will move the partitions around so that the partitions are balanced. And we know what balance means. Remember the pictures? So it will move the partitions around to balance it across the broker. So it's this very nice feature called self-balancing cluster. It's in Kafka, in Confluent Enterprise platform. Okay, so with that in mind, let's look at the lab. I'm going to give you a key right now so you can go to the environment. Here's the key. I'm going to put this with the URL into chat, and I'm going to do this with you. So here is the key that you need to access the environment. I have, okay. And the environment itself, now we have